Hello and welcome to today's webinar, Cascade Heating, Application Range, Sizing and Optimization. My name is Michael Hoeneß and I'm Customer Relationship Manager here at Polysan Villa Solaris. At first, a question to you. Can you hear me well and can you see the screen? Maybe you can use the question function to just give me some feedback. Perfect. Thank you so much. You can also use the question function during the webinar to ask any question, and I will then try to answer directly, depending on the situation, or in our question and answer session, which starts in 30 minutes. So let's start directly with a short view of the agenda. And we will start with the welcome and introduction, just a quick history of Polysan, and then we will dive right into the fundamentals of heat pump cascades. You will see the new Polysan templates. These are heat pump cascade schematics and heat pump system designs. And we will dive into some practical application examples. All of these we will do directly while looking into Polysan, and then in the end there will be a conclusion and a 15 minutes question and answer session. Let's have a look at where we are coming from. So Polysan is a simulation engine that started in 1975 when Martin Zock developed the first simulation models. As you can see here on the left-hand side, these were focused on solar thermal systems. And already in solar thermal systems, it's really important how much solar yield do we have on the solar collector and what temperature does it reach, what temperature do we have in the buffer tank, and then how much energy is actually withdrawn. So this focus on energy and temperatures we developed, that has been developed further. So starting in 1992, the models have been developed further in Switzerland, in Rapperswil, at the Institute of Solar Technology. And then in 2006, the company Villa Solaris was founded as a spin-off, and we have then developed further the models, including heat pumps, and as we're talking now about heat pump cascades, and also about any relevant technology in the building and district sector. Polysan and Villa Solaris is headquartered in Winterthur in Switzerland, and we are market leader in energy system design. We distribute our software Polysan in more than 40 countries. We have customers in most of the countries in the world. And also we provide expert services in energy system simulation. This means if you have any project you'd like to work on it with us, you can just get in touch. Here below you can find our contact details, info@villasolaris.com, or also our telephone number here. And we have more than 1,000 corporate clients that use Polysan. Amongst them are renowned engineering firms, contractors, energy service providers, and universities. Let's get now right into Polysan and the heat pump cascades and cascade heating. We will have a look at the fundamentals, different types of heat pump cascades, and then we will look at the new Polysan templates. We will take a look at the heat pump cascade schematics and the system design, and then we will dive into the practical application examples. So here in Polysan, you can see that you can filter in the standard templates by application and also by category. So application is, for example, hotel, commercial, industrial area, and by category. And here the first one is already heat pump cascade. there are 8 systems available here, which have different focus. And we will start also by looking at the 2 different types of heat pump cascades, which are parallel heat pump systems. So I will just open this one here, and you can see 2 heat pumps in parallel. And here we can see that 2 heat pumps are sharing the load, so they deliver the same temperature. And we can also illustrate that when running the simulation analysis here with the green buck symbol. And then we can actually see what's happening in this system time step by time step. So we can see Polysun is a dynamic simulation tool. And we can see that when both heat pumps are running, which power they are delivering and which temperature they are delivering. We have a process heat system in this schematics. So the heat is delivered at 72 degrees. And here now we have this parallel system, which focuses on redundancy. So now you have 2 heat pumps, they're sharing the load. If the load is lower, so cascades are really used for a high fluctuation of loads, and they share the load, and it's a redundant system. So if one stops to operate, you still have the other one, and also as there are 2 heat pumps running, they can always run in the optimal, in the sweet spot when running at partial load. Here, when we deliver a temperature of 72, that's actually also a good example which we can do with 2 heat pumps in series with a so-called booster heat pump, because that's a different system, and I will show you in the standard templates. Here we have also a template with 2 heat pumps in series. For example, this one here at the top bottom right, it also delivers process heat. So that's a Cascade heat pump schematic diagram for process heat, and with 2 heat pumps here in series. So this Cascade heat pump system offers these 2 heat pumps here in series, and which the first heat pump uses the groundwater as a source, and then has a temperature difference of maybe 5 to 35 degrees. You can adjust it depending on your needs. And then here the second heat pump system, the booster heat pump in this heat pump cascade, can bring up the temperature from 35 to 70 to deliver the right temperature here at this energy sink here. Then also, and this is already a look into the third system, or it's not a new type, it's basically a mix. So there's also hybrid systems. Here there's a hybrid system because we have a gas boiler that actually helps to get up the temperature to a certain level. And of course, we can also mix heat pumps in series and heat pumps in parallel. And then I can show you the Cascade heat pump schematic diagram also for an example of a hybrid system. So let's have a look. That could be, for example, this one here. I'm opening this for us. And here we can see that we have a commercial building. We have a hot water temperature. Here we need 60 degrees. And then we also have a floor heating here. And you can see now we have in this Cascade heat pump schematic diagram 2 heat pumps in parallel to deliver low temperature heat, which is then used in the floor heating. And then we use this booster heat pump here to bring the temperature up to 60 degrees Celsius. Of course, you can also change the units to Fahrenheit or other unit systems. In this case, we have 150 kilowatts here for the lower temperature and only 70 kilowatts for the higher temperature. This is common in systems where you don't need so much hot water and you need a lot of floor heating, like in this commercial building. So in general, heat pump cascade systems make sense when you have larger multi-family dwellings, when you have commercial buildings, when you have hotels with fluctuating loads, with varying loads, high peaks, and then you can combine several heat pumps here in series or in parallel. You can combine these cascade types to reach certain temperatures and also to just deliver the right power at the right time. So here we can see we have the redundancy for the lower temperature with these two parallel heat pumps. And then we have here again the booster heat pump. And this system ensures that each heat pump can run closer to the sweet spot than if you just use one large heat pump that at the same time needs to deliver the heat for the floor heating and the heat for the hot water, which of course is also possible. Someone just said the sound disappeared. Can the rest of you still hear me? Can you just let me quickly know in the questions? Okay, so I think it's just I will just write him to log in again, maybe. And also let us have a look at the simulation analysis to see exactly what Polysun is doing. We will be able again to simulate 1 year. So the simulation is running now and we can have a look into any time step here. And now you can see that just this heat pump here is running. It's running at a coefficient performance of 6.28. So it's pretty efficient right now. And it's bringing up this this buffer tank to 37.9 degrees Celsius. So there's no need right now to switch on the second one because we don't have extreme temperatures and we have our buffer tank at a good level. And then you can see also here, because it's red means that there is some load flowing through the pipes. So you can see the floor heating is active now, and also the hot water is active. And only once the buffer tank for the hot water goes down the temperature level, then the booster heat pump switch on, bringing down the temperature in this buffer tank, and then also it might bring the second heat pump to switch on. So you can see I can click through these time steps to see what is actually happening in the system, and I can also move this to go further. Now the second heat pump here is running. They can also switch on alternately or simultaneously, as here the whole system is running. The two heat pumps here are charging the buffer tank, and the booster heat pump is running to bring up the temperature in the storage tank. So, of course, here we have a system that's split it into several heat pumps. It has advantages to just using one, because if you just use one, you have one large component that needs to run at, needs to deliver to really different loads, different temperatures. So if you split that into several units, you can just have one unit doing a special thing, running at their sweet spot. So it has a lot of advantages. It's also easier to source. You can just get smaller heat pumps from typical heat pumps, and you don't need an individual made industrial heat pump, for example. So that's another advantage. But of course, rather than just plugging in one big heat pump, in this case, you really need to have a control system set up that manages all the different heat pumps and their different purposes. So let's have a look at the control system in place here. You can see there's a programmable controller working with this booster heat pump. And when I double click on it, then we can see here the operating stages. It's on and off in this case. And here on the right-hand side, we can see the conditions that bring it to switching on and off. So it's basically coded that when as soon as the storage tank layer falls under a certain temperature, then the heat pump switches on. What you can also do is you can have a inverter control heat pump with a variable temperature that delivers variable load, and you can also include that here in the programmable controller. So of course, when you have these systems set up with multiple heat pumps, then you can save a lot of costs, because the heat pumps itself, they run efficiently. They are in itself, they're less expensive to set up than just one big heat pump, which needs to be specially constructed for the case. But of course, you also need to set it up correctly. And when you set it up correctly, you can save up to 40% of the costs than just installing an oversized heat pump that run inefficiently and that breaks early due to wear and tear. At this point, let us have a look at another example and another template. I go back into the standard templates here, and we can see an example for a school, another typical example that is used when heat pump cascade systems are used. So here you can see there's 4 different heat pumps. 2 heat pumps are 40 kilowatts, 2 heat pumps are 10 kilowatts. And of course, we could also build instead one large heat pump that caters to this buffer tank up here and to the buffer tank down there at different temperature levels at different times. But then it's there, you don't have any redundancy. There's it doesn't run efficiently because maybe you need really low amount of power, and usually large heat pumps, they can only go down to a certain minimum of power. And here with the 10 kilowatt heat pump, we can go to 10 out of 100 kilowatts. So that would be as much as going down to 10%. And even if you run that variably in inverter controlled, you can even go lower to, let's say, 3%, like 3 kilowatts out of that 100. So with this setup, you can control the power and cater to varying loads, and also to peaks, and also to partial loads where it comes really effective. And you can see each heat pump has their own control system here that controls to which tank it's actually loading the energy, the heat, and which are the conditions for it to switch on. And this school is a good example because we have a school and also a sports center to it. And of course, the sports center needs also showers, so we have that here. And then there's 2 types of heating, and also the opening times, they're different, of course. So there's some times when maybe the school is closed, but the sports center is still used. So that's why it makes sense to have this setup with different heat pumps that also can be switched off at different times and can be maintained at different times. So this is another good example for a cascade heat pump system. Let's have again a look at our template and hybrid systems, which is the combination of heat pumps in series and heat pumps in parallel. They also come in cost effective in a system with a lot of different loads, and if you also would like to use the waste heat, bring it to a different level. Let's have a look at the district heating usage here. And here you can see there's a large number of consumers on the right-hand side. We have the building here together with the hot water, and also we have a pool, again, of a sports center, and then we have a large combination of different consumers and different heat pump cascades. So in this cascade heating system, we have, for example, here the source temperature that is from the wastewater heat exchanger. It might be depending on the location. Maybe we have it at 5 degrees, and then this heat pump brings it up to the temperature necessary for the floor heating, which might be 35 degrees. And then in this case, also we have an electric boiler bringing up the temperature for the hot water. So you can combine all the components here in Polysun, and also here we have a gas boiler again here in parallel with this heat pump to bring up the temperature to the heating controller here. It's actually also mixture of series and parallel, so here to bring up the temperature necessary. Let's have a look at the heat pump catalog. So here we can go into the catalog of the heat pump, and you can see there's a lot of different manufacturers. So there's a lot of data already in Polysun, different components. There's also anonymous heat pumps. Here you can just see the power of the heat pumps in the name. And then there's two ways of defining the heat pump. One is just to enter the specifics of the heat pump here. It's always described by two pairs of temperature and power. So it's temperature on the primary side, on the brine, for example, temperature on the output side, and then heating and electric power. So basically the coefficient of performance is defined for different temperature ranges and different power ranges. And if you want to be more individual, you can also just enter the file name here as a CSV file. So then you can define the temperature pairs yourself. For example, really high temperatures or also partial loads can be defined there. So in Polysun, what matters for the behavior of the heat pump is this specifics included by pairs of heating power, electric power, and temperatures. So when choosing the right heat pump, then you can just go into the catalog, make sure the specifics match your needs, and you can also find the heat pump by a manufacturer by just entering the name here in the search field. Let's have a look at the other templates we have just published with one of the latest releases. So there's also here this combination of a heat pump cascade system with hybrid solar panels combining solar thermal and electric systems, and a ground source loop. So here we have an example for an industry process system that's using a seasonal storage here, this ground source loop regenerated by the hybrid solar thermal collector here, and then a cascade heat pump system with two heat pumps in parallel, and here another one in series to bring it up to the necessary temperature, which is 70 degrees in this case. And let's have look at the last two templates that you can find in here, which are new. So there is this one that combines cooling and heating. This is, for example, relevant in hospital systems. Here we have a process cooling that's needed in this hospital. And we have this air-water heat exchanger to get rid of excess heat in summer, for example. And then the heat pumps can operate either for the cooling process or for the heating process, and can use both the buffer tanks as sinks or sources. So we have a thermal network here that uses the heat where it's used best at the right temperature. So we can use the cooling as a waste heat for the heating, and use this booster to bring it up to another temperature level for hot water. So you can make the combinations here to have the right system. And then another new system here is the space heating system, also combined with the solar thermal hybrid panel here. And this is another of the new Cascade heat pump schematic diagram. Let's move on in our agenda. We now went through the fundamentals of heat pump cascades. We have seen there's different types. There's parallel heat pumps, there's series heat pump cascade systems. We looked at the schematics and the system diagrams, and we also have looked into practical application examples such as heating districts, schools, hospitals, and industry systems. Basically, the key takeaways now are that the heat pump cascades, they're flexible and redundant. So you can combine parallel heat pumps to have a redundancy, and you combine it with series heat pumps to be flexible, to deliver the heat you need at the right time. You can have a modular approach to it, so you can have another heat pump added for a different temperature level. And then we have also seen that there is a high efficiency and lower costs if you design the units correctly. So if you run them in their optimal range, if you design the system correctly, then you can cut energy costs and operating costs and installation costs, investment costs in general. And due to the higher complexity we get due to the heat pump cascade systems, reliable planning is necessary. So we need a simulation software such as Polysun to do dynamic simulation and ensure the optimal sizing of the components, hydraulics, and control strategies. Because if we don't do it, we oversize the component, we oversize the heat pump, which has a lot of costs. It can unnecessary costs. And also, if the heat pumps don't switch on at the right time, if the control strategy is wrong, we also have efficiency losses there.